4.1 Sampling and Surveys. In statistics, we often take a look at two things: the population and the sample. The population is all of the individuals we want information about. This is represented by variables like mu, sigma, and p. A sample is a part of that population, which we represent through variables like x bar, s of x, and b hat. In statistics, we often take data about the sample, in which case we use to make inferences about the population. When planning the sample study, we both need to figure out the population and the variable of interest. There are multiple things that we can do that makes our samples bad or results in bias, which is a systematic problem in a study that favors a certain outcome. The most common is a convenience sample when we only choose individuals that are easiest to reach, voluntary response samples when only people who partake in a study are the ones that wish to be in the study, which in case causes people with strong opinions to respond, and non-random studies when the sample is not random. When we don't use randomness, we often create bias by selecting certain individuals to be in the study over others. There are three types of samples we usually use to make inferences about the population. The first and most common is a simple random study, or an SRS. An SRS of n individuals in which it is a case in which every individual has the same chance of being selected for the study. Say you have 50 people and you take a random 10 of them to be in the study. Often you'll use table D of the random numbers in order to assign individuals to the simple random study, and you choose those people to be in the study. Stratified random samples are when group populations in a group. When you take a group, you group the population into groups of similar individuals based on a same characteristics, which are called strata. After this, you take an SRS in each strata, and you combine each strata into a full sample, and then you do the study on the full sample. We use this whenever a characteristic could influence the response. Instead of doing a stratified random sample, we could also do a cluster sample, in which case we divide the population into smaller groups, but this is not based on a similar characteristic such as a stratified random sample. The main difference between the two is a stratified random sample, we break them up into groups of similar characteristics, and a cluster sample, you do not. After you divide the population into smaller groups, you take an SRS of each cluster and combine the samples into a single sample, which you do the experiment or observational study on. Now, the reason we do sampling surveys is for inference. In order to get data from a sample, we get data from a sample, and we use this to make an inference about the population. There are two problems in inference when there are two problems in surveys that happen that could result in bias. The first is undercoverage, which is when some of the group of the population get left out of the study. This results in the population being skewed to the groups that are left in of the study and results in inaccurate inferences. The other problem is non-response or non-response bias, when certain individuals choose not to participate after they've already, been chosen to be in the study, which again can result in undercoverage by certain groups of people not being represented in the survey and creates inaccurate inferences.
This is important as kind of a building block for a lot of more advanced statistical procedures that you'll get into later. So first, it's important to understand the difference between an experiment and an observational study. Now, they're both going to collect similar data. They're both going to observe individuals and measure the variables of interest. The main difference between an observational study and an experiment is that observational studies don't influence the responses of individuals, whereas experiments do by assigning individuals to different treatment groups and recording the effects of those treatments. This means that while both studies can conclude correlation, that two variables are related, only experiments can conclude causation, that one variable changing causes a change in the other. There are a few types of variables it's important to understand when talking about experiments. First, your explanatory or your independent. This is the variable that's changed by experimenters. For example, in a drug study, this is the medication subjects receive, either a drug or a placebo. Then the dependent variable. This is your y variable, the one that has its changes measured, and the hypothesis proposes changes as a result of the explanatory variable. And so in that same drug study, this would be the health of subjects after receiving the drug or the placebo. Obviously, you're looking to see if changes to the explanatory, i.e., what drug is received, change the response of the subject, i.e., the response variable. Now, there are also lurking variables. These are variables that could affect the response but are not included in the explanatory variables. And a lot of experimental design's goal is to eliminate these lurking variables as much as possible. A few more terms. Treatment, that's a specific condition you apply to each experimental unit. An experimental unit is the smallest collection of units that a treatment can be applied to. Subjects are what we call experimental units when they're humans. And a control group is a group of experimental units that receives a treatment of no change. For example, in a medical experiment, they're given a placebo. This is important for us to compare groups given specific treatments to. Randomizing experiments. Experimental groups, you want to randomize them because this helps eliminate as many lurking variables as possible in the experiment. The way you do this is through random assignment. You assign experimental units to treatments at random using some form of random chance. This can be digits from table D. This can be randomly drawn cards that assign a unwitting subject to control or treatment group. It just has to randomly assign these subjects to treatments in any way. And now if you perform this random assignment properly, you'll end up with a completely randomized design, which is an experiment where all treatments are assigned to subjects completely randomly. This is the best experimental format for eliminating lurking variables. There are also a few other types of experimental design to know. For example, a block design, which splits people into or splits experimental units into groups before the experiment begins non-randomly. For example, splitting subjects by men and women, and then randomly assigning treatments within that group. These allow you to test more specifically to determine the relationship between variables in each of these different subgroups or blocks. Matched pairs design is a form of blocking that randomly matches pairs of similar experimental units and gives each pair the treatment in random order. A single blind study is one where the subject doesn't know what treatment they received, but the experimenter does. Double blind is where neither the subject nor the experimenter knows what treatment the subject has received. And double blind studies are typically more reliable than single blind studies because they eliminate more potential sources of biased data. This all boils down to really three principles of experimental design from which all the rest of this comes. These are the three things you really need to know. First, an experiment needs to control for as many lurking variables as possible before it begins. Using comparative design, your goal is to ensure that the only systemic difference between the EUs is the treatment they receive. Second, once the experiment begins, it has to have random assignment, using random chance to assign treatments to EUs. And like control, both 1 and 2 here are designed to balance out the effect of lurking variables on the experiment and eliminate them as much as possible, so all we're really looking at is the explanatory variable's effect on the response. And third is replication. You want to have a large enough sample size, use enough experimental units in each group that the results of the experiment can be reliably repeated by following the same procedure. This ensures that the data reflects a statistically significant and real correlation and isn't just a product of random chance.
4.1 and 4.2, you were learning how to create studies. Now in 4.3, we're going to learn how to utilize those studies in order to draw conclusions. So when drawing inferences, there are sort of two different inferences that we can make once we've made our studies, but we have to answer the questions of, were the individuals of our study randomly chosen, for instance, with a simpler random sample, or with other methods learned in 4.1. And the second question is, were those individuals randomly assigned to groups? So once we have collected the individuals from the overall population, we have our sample size, were those individuals then randomly separated into groups? So in observational studies, when you're not assigning treatments to certain groups or creating groups, the answer to the second question is always no. And that's just because there are no groups in observational studies, merely because you're not testing, you're not assigning treatments to anything, so you cannot extrapolate that answer to be yes. So from these two questions, we can sort of make two inferences. The first is the relationship of the sample to the population. So so we can sort of determine, is the sample representative of the larger population, which is one inference we can make. We sort of want to know if our sample can sort of tell what is going on with the larger population. And the second inference we can make are sort of drawing cause and effect relationships. i.e., does the treatment cause a certain outcome? Or if we assign this treatment, we will expect to see this in the future. So, if the study or experiment had individuals that were randomly chosen through an SRS and another method, then the results of the sample mirror those of the overall population, which makes sense because if you had randomly chosen individuals, then you would expect all aspects of the population to be represented within there, which means you can extrapolate your sample to be part of the larger population that you're looking at, which means if the answer to were the individuals randomly selected, you can make generalized conclusions about the population. And if the experiments of the groups were randomly assigned, cause and effect relationships can also be made, meaning that even if you didn't have a random collection of individuals from the overall population, as long as you randomly separate those individuals into two separate groups or more than that many groups, the two groups have the same characteristics because they're random, which means that the only difference in the outcomes of that must have been because of the treatments. And observational studies can never make cause and effect relationships, which means we have to have experiments in order to do that. But sometimes it's impossible to make cause and effect conclusions with experiments. So an example is, does COVID-19 make people feel worse? Well, the obvious answer is yes, but we can't test this using an experiment because in order to do that, we have to give people the coronavirus, which is probably unethical and we can't really do it. So in that case, we can make causation statements using indirect evidence through observational studies, and we can use things like dissociation being strong and consistent, more treatment, more outcome, more time with treatment, meaning more outcome, and the plausibility of these factors. So for those four things, we can see with our coronavirus example, we can see that people with coronavirus generally are less healthy. If they have coronavirus and they're older, they obviously have more adverse health effects. More time with coronavirus obviously makes you feel worse, and it's clearly plausible because coronavirus is obviously bad. So even though we didn't have an experiment to test that, we can still make those conclusions in an observational study, albeit indirectly. And the last thing we have to consider is sort of ethics within statistics. So for the same reason that we couldn't assign the coronavirus to do an actual experiment in our last example, there's plenty of examples like this, such as vaping, smoking. When we're trying to test the health effects of something harmful, we obviously don't want to subject individuals to those sort of things. Furthermore, we don't want to place treatments onto subjects that they don't want, which means informed consent is also important, and confidentiality of the subject's sort of past medical records, health effects, outcomes of the treatments, etc., should all be kept confidential.